to unified conferencing.
Stuff actually, I think the 2-pyridyl is one of the problems that he's actually solved well with midas. It's kind of impressive how well it works.
Actually, the best solution for the 2-pyridyl moronic acid problem is just adding copper. There were 2 Merck papers on that problem. Well, we can send it out if you want.
I think the one thing with the copper solution is it solves the reactivity issue, but it doesn't solve the storage issue. Because if you want to be able to store that moronic acid with 0 intermediate or by it, that's why I would like to do midas. So you take one step to the side in the other direction.
Get up a notch, though. So I got a bunch of how to use this molecule
approximate. Maybe not the difficulty of the Merck compound, but I think the Pfizer compound. But like, you don't need to come. I think the difference is like what an acceptable answer is. Like, it doesn't need to be a full retro forward. It needs to be like, oh, I see this reasonable disconnection, and I can break it into at least these two parts kind of with me.
No, 1 minute. Okay, it's 8 o'clock. It's time to get rolling. Can everybody in Florida hear me? Yes, okay, great. Okay, so today we'll talk about the least expensive way to do CH functionalization on pyridine. And it's very old, and it involves deprotonation. But it's not that simple. So it's definitely not as simple as you may predict, and hopefully over the next hour, if you're not thoroughly confused, you'll at least realize that there's an enormous variety of things one can do with deprotonation strategies. As we mentioned last time, when you make pyridines, you're going to have this question in your head, do you make it or you buy it? And the strategies I'm going to show you today allow you to make many, many things so that you won't have to actually make a pyridine ring. All right, so let's start with a case study. And what we're going to do a lot when we talk about making rings is these cage matches between the process chemists and the med chemists, which I don't know if they get physically violent at Lilly and Pfizer, not often maybe. HR steps in. But, this question of why is it that medicinal chemists do things differently than process, because they're sort of dictated by speed and getting the biological answer as fast as you can. So 2% yield is enough if it gives you 2 mgs for the bioassay and you know whether the answer is right or not. And maybe many years ago there was a stigma against med chemists like, oh, they give us these bad routes. But actually, as you will see through this class, their med chem routes are often fit for purpose. In many cases, you can't take a process route. It will be useless to a med chemist. So we'll see many examples of that through the class. So what kind of disconnections will we make to this piece? Obviously, the 3 pieces. It's going to be triplet convergent. But what sorts of disconnections do you think are kind of immediately obvious that you might want to make in a molecule like this? What do you say, Max?
I guess the amide on the far right side.
All right, let's get rid of the amide. So we're going to break here. Any other disconnection?
And then somehow chopping off the linker between the both 2 heterocycles. So I guess that's nitrogen and the.
So maybe like that. And that gives us 3 nice little pieces. And the 3rd piece. Okay, so let's focus our attention on compound A. Tiny little pyridine, looks pretty easy. I mean, today you may be able to buy it from Combi Blocks, I don't know. But back in 2004, I don't think so. And so if you're a med chemist and you need to get this very quick using everything we learned yesterday, how would you make it? We have the pyridine team. Maybe they can come through for us. Steve, Dongmen, any suggestions from yesterday's notes of how you would go about making quick and dirty?
Pyridine and oxide nitrile reduction.
Brilliant. Take this guy and reduce it down. Great. Tanner, right?
Yeah.
But you move spots, so it screwed me up. All right. Great. What's the problem with this, do you imagine? MedChem is fine, but what about process? Why would process not just take this route and go with it?
TMS cyanide.
One problem is TMS cyanide. Another one? Regiochemistry. They get 3% of the other isomer. Exactly. 3%, med chemists are like, who cares? Process chemists are worried about the parts per million. So 3% is a lot. Can't be doing that. Any other issues? I mean, N-oxides, you can use them on scale. We'll see an example of that. But if you can avoid them, they often are high-energy intermediates. They usually are things that process chemists want to avoid. So if they can avoid a pyridine oxide, they will. Sometimes it's okay. But those are the three problems with this med-chem route. What do you think the process chemist approach would be? I mean, let's start with the exact same starting material. What would be the most rapid way, based on the title of today's lecture, let's just deprotonate. If you could find a way to deprotonate, that would be really swell. Well, it turns out there is a way to do this. And what we have to think about first are the innately activated positions of pyridine. So here in the corner, you've got just the native pyridine. And when you've got regular pyridine by itself, the kinetic preference for deprotonation is going to be the metal, first thing it sees is, wow, there's a lone pair there, it goes right there, and then deprotonates here kinetically. But then if you give it time to think about the situation, it's like, wait a minute, this lone pair, I'm at negatively charged, I'm an LDA or whatever I am. I'm not really enjoying this charge repulsion. On second thought, maybe I should go here. And this is a thermodynamic spot. And you can control the site of metallation by changing the conditions. And we'll get into that in a little while. So by changing solvent and temperature, you can encourage either thermodynamic or kinetic. Even the base has an effect. So for instance, if you want to use what they call Fat Albert, or lithium TMP, big old base, low temperature, ethereal solvent, you might prefer to go kinetically. But if you use something like LDA, 0 degrees, you're going to go thermodynamic. Use THF as a solvent. Now for the test, or for the real world in an interview, you just say, I'm going to deprotonate under kinetic conditions, or I'm going to deprotonate under thermodynamic conditions. You don't need to give people the exact reagent conditions for the transformation. It's enough to say thermo or kinetic. Now the situation can change because you don't often start your syntheses with just pyridine. So things have directing groups, and those directing groups can be innate on the molecule. For example, fluorine is a reasonably good, a moderate directing group. But other things can be really good directing groups, like Vic Sneakus has pioneered the use of tertiary amides as great directing groups for metallation. So if we have a directing group at C3, you will you're going to, very quickly, very easily deprotonate right here. If you have a directing group here, it's obviously going to go here. And if you have a directing group here, it's going to go here. It's kind of intuitive. Just think of the directing group like a little magnet that's magnetized. The base comes in, it sees the directing group, and then it goes adjacent. In pyridine, remember that the C4 position is already the most acidic. Okay? Now, when you think about deprotonation and using it in synthesis, there's an interesting way to design your retrosynthetic analyses based on the substituent pattern that you've got. And couldn't find this in the literature, but sort of just thought about all the examples that are out there. And the way that comes to mind that's easy for at least me to remember, you may choose to do something different, is this sort of spectrum, substituent spectrum on pyridines and heterocycles in general. When you have an aryl or an alkyl, generally those things are disconnected at the beginning, meaning they happen at the end. And generally when you have something like a fluoro or chloro, those are disconnected at the end, meaning you either buy them or they're put in at the very early stage. There's two special features of some of the ones we've got here. The chloro is often used as both a directing group and a disposable entity that can be removed. So people will often put chlorine there as a placeholder, use it to direct something adjacent, then discard it. People often use a TMS. You never really see very often TMSs in final drug substances. But people will often embed TMS into their root because if we put TMS, let's say, here or here to make it easy, you can't get lithiation there because of sterics. So it will prefer immediately to go there. So TMS is a great way to block. It's kind of like the umpoled magnet. So the base goes near it. It's like, whoa, I'm getting out of there. And it goes further away, one position over. So you can often install silyl as a way to block a position and then at the end remove it. Just like chlorine can be disposable just by removing it with palladium on carbon, or if the chlorine happens to be at the C2 or the C4 position, you can use something like zinc and acetic acid. So to illustrate this feature, let's take a look at the case study number 2 on page 37 of your book. So there's a few case studies at the end of the pyridine section that I think will be somewhat helpful to you if you haven't already taken a look at them. But here are some of the retrosynthetic thoughts on this. And this is a natural product, and obviously the natural product can come back from the corresponding aldehyde, just make an oxime. And then you have a tactical decision, and the tactical decision is rather equal because you're not sure about the relative selectivity. So this can come by either a formylation or perhaps an arylation, either one. So the key decision that you're going to make is, well, we can probably start from a dihalo and then differentiate either the lithiation followed by formal quench or Suzuki coupling. And then this comes back from here because you can imagine this is a great directing group that we can put a boron and then oxidize it to the hydroxyl. And then finally we can get all the way back to 3-hydroxypyridine because we know we can do dihalogenation. So in the forward route, here's what it looks like. You take the 3-hydroxypyridine. You know this is prime. Just pretend it's a phenol. You know it's prime for diiodination. That happens in pretty good yield. You then put your mom group there. The mom is a great directing group for directed lithiation. When you treat it with a standard base, quench it with a boron, and then oxidize it off, you now have your phenol. You then put a methyl group on there. And then in the next step, they found that they could get selective halogen metal exchange. And that probably happens because, again, the mom is here helping you out. The mom is like a magnet, remember? Brings in the metal. You now have a zinc species here. You do a standard Negishi coupling, and you've got that. And then the end of the story is just halogen metal exchange, quench with a formal, and then make the oxime. Very simple. This is this is the simplest we're going to get here. Things can get more complicated. For example, what if I tell you I want all the isomers of this fluorocarboxylic acid, and you don't have access to anything other than 2-fluoropyridine? Let's imagine Combi Blocks is out of business. Steve, Dongmin, can you tell me, how about the first, just give me the first one? So that should be fine, right? Then quench with CO2. We're good there. How do we get this one?
Switch the
you could
character.
either try for thermodynamic, but you're going to have a competition because in this case, the thermodynamic is really this one. So you're going to find yourself in a bit of trouble when you try to deprotonate directly at C4 when you've got this fluorine like a magnet tracing everything to C3. So how would we make this the favored one? Let's put a chlorine. So retrosynthetically, you would go back to this. And then this one comes from put a chlorine, lithiate again, and then take off the chlorine. With palladium on carbon, hydrogen is fine. How about this one? We could use a TMS. You have two options here, folks. You could do that, or you could make it a dichloro. So you could take this compound, chlorinate again, and then lithiate again, and then quench, and then palladium on carbon. So two options. Both are correct. How about this one? Do we already have something drawn there that might help us? Maybe? What do you say there, Max 2?
Well, you could go on further and just walk all the positions sequentially.
Yikes! Yeah, polychlorinated. Yeah, you might be able to. I can't say no to that. Is there a more elegant solution to it, perhaps?
The N oxide and then cyanate. And just hydrolyze it.
You could certainly. Yeah, that's not a bad idea. If you want to avoid, let's say, you're a process chemist, though, you don't want to do that. Direct off the night. Well, the problem is that directing group is like a magnet. It's really hard to totally override it. So if you want to be guaranteed on paper you're going to get the correct one, try using an intermediate that's already written here.
Can you use the TMS lithiated species, chlorinate that, and then use that to direct?
You certainly could. Yep. So one suggestion would be make this guy certainly fine. That would pass muster on any test.
If you had just the TMS, would it be kinetic to form that lithium without the extra chlorine?
If you only had TMS here, you mean?
Yes.
And I bet that I can't say that would not work. Yeah. I can't say it wouldn't work. That you could, if you put it on a test, it probably would. We couldn't mark it off. I just don't know because based on first principles, it's reasonable. What Tucker is saying is that if you just had this species and you did instead of a regular lithiation, you did let's say a kinetic type lithiation there. It's reasonable. The other option would be to just take this compound and throw a TMS on it, then lithiate again. That was another option. So we have three options. Super. Questions?
Can you first put a hydroxyl and then use the hydroxyl?
You want to put a hydroxy where, Cheng?
This three position. And then the direct halogenation of the straight hydroxyl.
Yeah, it's just you're going to have hydroxylation. It can happen here or iodination here or here. And then you have to do another cross-couple, and then you have to do lithiation of that. And then how do you get rid of the oxygen? Make the triplet, and then, it's long. And so when you're thinking about the test, which is kind of like a mock consulting session, if you find yourself doing multiple steps to do something that's kind of simple, just stop and say, Phil couldn't possibly mean for us to do that. So you're rarely going to see people install a hydroxy and then remove a hydroxy. I'm sure you'll find in a SciFinder example of somebody doing that, but it's not great. Okay, any other questions? We're going to keep doing this a lot, so if you're confused, don't worry. Hopefully, and I have good news for you, actually. The review session, which will happen in 2 weeks, Yuzuru and David are going to focus only on pyridine substitution, because this is a really complex topic, and there's so many different derivations of this. So whatever you don't understand today, don't worry. In 2 weeks, we're just going to focus on that for an hour. Okay, why don't we take a look at problem of the day number 1 before we go on to the next case study. Questions, Florida?
Yeah, can you just carboxylate pyridine at the kinetic lithiated position and then fluorinate?
You're talking about instead of doing all of this, install the fluorine by lithiation and quench with the electrophilic fluorination agent. Is that what you mean?
Yeah, we'll first carboxylate at the kinetic position and then fluorinate second.
You mean for this last derivative here?
Yeah. Okay.
The issue with that is that the carboxylate and the carboxyamide is the good directing group, and so it will likely go here. So the same exact problem we face with starting from fluorine and going to CO2 is what you would face if you wanted to go from CO2 to fluorine.
Okay.
Because essentially you've got a couple of positions. You can either go here, which is probably thermodynamic, and in this case the kinetic probably switches to C4. This is probably a third or fourth position to be lithiated, because you've got this good directing group here.
Okay, thanks.
Yep, great question. Problem of the day number 1. Looks kind of similar to what we've been doing. Who's going to help us with this one? Saul, you want to give it your best shot?
I mean, I can just talk through it. I think.
All right, let's talk through it. If you want to talk through it.
Kinetic deprotonation followed by carboxylate quench will be the first one.
For the first one, we're just going to deprotonate with whatever, like LDA or something. Okay.
Thermodynamic will go to the second one.
Thermodynamic deprotonation for the second one.
And the third one, we can play these same kinds of tricks, like chlorinate at the 4 position after a thermodynamic lithiation, and then it should be directed there.
Sounds good. And let's imagine you had a problem differentiating the thermodynamic and kinetic. What would be the trick you would use there?
Block whichever it goes to with TMS if it's a problem.
Well, you don't want to use TMS for the top one, but for the bottom one, I guess.
Oh, you're saying to make the third compound?
Yeah.
Yeah, so if it lithiates too much at the 2 position, then you can block 2 position with TMS. And if it lithiates preferentially at the 4 position, then you can activate that with chloride, or activate the 3 position subsequently with chloride at the 4 position.
Sounds good. Did everybody hear that? Everybody get it? Okay, great. How about this derivative here from Pfizer? We need some disconnections first. This is way before your time, I guess, Patrick, right? Interesting little compound. Again, a triply convergent approach can be imagined. And we need to break it into 3 pieces. And the clue here is that process chemists will very rarely do this type of coupling, but in this particular case, it's the only thing that worked. So there's a particular coupling in here that was used. Zhang, any suggestions for some key bond disconnections?
I'll disconnect the secondary amine. The secondary amine from the pyridine ring. And I guess the last one would be cutting up the 2 heterocycles together.
And then the last one would be doing what?
between the two heterocycles, yeah.
Okay, so you may be rather shocked when I draw the structure. In this case, Stille is the only thing that worked on scale. They tried everything. And you'll often find that in the case of things like imidazoles. I mean, retrospectively, I think you can come up with a better route to this than using a Stille on scale. But we'll talk about that, I guess, when we start talking about azole synthesis. And when you have lots of nitrogen content, these types of heterocycles often, Stille is still really good. Some medchem departments still do Stille no problem. They're not afraid of it. How about Lilly at Pfizer? Are you allowed to do Stille if you want to? Yeah. Pfizer's okay. It's discouraged, yeah. The tin. But, I mean, if you can adequately purify it away, it's not that big of a deal. Okay, great. So how do we make B? That's the key intermediate we need to make. We'll start from aminothiophene, and we treat this with triethylorthoformate in the presence of Meldrum's acid. And that delivers the following adduct. Which, when you heat it up 240 degrees, does something pretty cool. Form an acyl ketene is what Hannah says, and then that closes. Just by loss of CO2 and loss of acetone. Okay, now when you treat this with oxal chloride and DMF, that goes through a Vilsmeier reagent. You turn that intermediate into what? And how do we take R equal to H and convert that into iodine? What do you say, Tanner?
Deprotonation.
Let's just deprotonate it. LDA will work. Even Bewley works fine. NIS, I2, all fine.
On process, do people generally like oxal chloride over POCl3 for these kinds of pH-intuitive chlorinations, or it's just like whatever works? Better?
I've seen a lot of both, and I've seen POCl3 used so many times in process that I can't imagine they have a big problem with it. And but I've seen them use Vilsmeier too, so I think it's just probably a whatever works kind of scenario. Good question. Okay, so we have our key building block B. And before we get to our building block A, it might be good to review something that hopefully you can commit to memory and never forget, at least until the end of Heterocycle. And that is the ease of deprotonation, generally speaking. This, as we've seen with the thiophene example, pretty easy to deprotonate. This, as you'll recall from the Vincent maneuver, is very, very easy to deprotonate. In the case of 5-membered ring versus 6-membered ring, the 5-membered ring is actually a lot easier to do, like thiophene, versus a 6-membered ring, and that has to do with geometry and electronics. So geometrically, in the 5-membered ring, the lone pair is really pointed further away from the site, and you get a stabilization. Whereas in the 6-membered, it's pointing into the base, and there's a charge repulsion. So for a 5-membered ring, let's say an indole with a protecting group on the nitrogen, or a pyrrole with a protecting group on the nitrogen, or a thiophene, really happy to deprotonate, no problem. Not a thiophene wouldn't be that, but imidazole, for instance, would be an example of this. But in the case of a 6-membered ring like a pyridine, it's a lot harder, as we just talked about over here. We see this often in tests. People will treat an indole or a pyrrole with Bewley and then say that they're getting lithiation here. Don't do that. It never happens. It will never happen. So if you deprotonate that NH, you can't get... That's actually, as we'll see in a moment, is a great way to protect that position from lithiation. Okay, so how do we make compound A? Suggestions? Take a look at the chart here. Take a look at the structure of the N-methylimidazole. And give me some suggestions. Deprotonate where, Max?
Pull between the two nitrogens.
And then what?
Well, it's not the right.
It's not the right one, is
You
it?
need to protect it with like TNH or something. And then deprotonate again and extract with the TNH.
That's your route? That's your route?
Yeah.
It's reasonable. I mean, on paper, it's fine. That's what you could propose. No problem on a test. It'd be fine. It's not what they did. They just went for the jugular. They dilithiated this thing. And they turned these both into the tin. So they now have a distanylated imidazole. How do you convert that now you need to go back to lecture 2 to understand the next step. How do you convert the distanylated imidazole into the exact imidazole they want? So now I've got tin at the 2, and I've got tin at the 5. How do I get only the 5 and not the 2?
Maybe you activate that nitrogen.
Can you do what?
Like protonate or like activate that nitrogen just to make the undesired tin more reactive towards action or something along those lines.
Well, let's go back to yesterday's class. If I treat this with thiophenol, where does the SNAR happen? Hannah? In between the two nitrogens. And if I treat that with zinc and acetic acid, which of the chlorines do you think goes away in between the two nitrogens? If I have a boron at both of those positions, which one do you think will proto-deborylate faster in between the two nitrogens? If I have a tin and I treat it with acid, which one do you think will proto-destanylate faster in between the two nitrogens? And so you can just take that distanylated thing add a little acid, proto-deacetylation happens upon workup at the C2 position, and they get out the C4 one they desire. Now, I'm not advocating this is the best way to make that compound, but we have to trust that the process people at Pfizer back in 2003 knew what they were doing. Let's take a look at some interesting case studies. If you take bromoimidazole and treat it with T-butylate and then an electrophile, what happens? I'll give you as many as you want, Hannah. Give you as many as you want. Tell me what you're thinking. You can use 10, 20, 1, 0.1, whatever you want.
Well, the first one's going to deprotonate the NH.
So your answer is what?
Nothing.
You just want, well, I add an electrophile.
Yeah.
So,
On nitrogen.
well, what if the electrophile is benzobromide? I mean, I put an electrophile. So
Sure.
your answer is either this or a proton comes back.
Yeah.
How come if I add 50 equivalents of T-butylate, not recommended, how come you didn't deprotonate here and then halogen metal exchange?
You told us we aren't supposed to do that.
I told you you're not supposed to do it here. Can you do it here? Yeah, you're looking at me like, and you're right. You wouldn't do that. It's way too not going to happen. So the only possible answer here from what I've taught you so far is what Hannah said. But the surprising feature of this is that halogen metal exchange is so rapid, it can even happen in methanol solvent. Yeah, it's really, really quick. It's like diffusion control. So the answer to this problem is that. Believe it or not. Chang, you're going to take that oxazole for us, and you're going to deprotonate it with butylate. And tell us where it's going to deprotonate. What happens? All right, perfect. And then where does my TMS go? Should just go to the carbon, right? Yeah. So the product of this reaction is this. That's what you meant, right? Yeah. How does that happen?
I guess the electron won't here kick out the I think it should go the other way.
Oh, you want to go the other way?
Yeah.
Well,
Nitrogen, yes.
oh, yeah, okay. And then quench with TMS. Yeah, that's a shame. Is there any way we could solve this problem? What if you really want that C2 TMS oxazole? Aha, that's it. So Steve just invented a JOC paper. That was a Vedas paper a long time ago where his solution to the problem is just add borane. Now you can lithiate all day. Quench with TMS, no problem. So for oxazoles, you need to use that trick. Sometimes the distinction between kinetic and thermodynamic can be difficult to predict just on a piece of paper if you've never seen it before. For example, this pyrimidine dichloride, the thermodynamic and the kinetic may not be what you think. So based on what we talked about before, you would think that the kinetic one would be next to the nitrogen. But actually it's the opposite in this pyrimidine series. So this one's the kinetic, and that's one the thermodynamic, meaning the conditions you would use for kinetic and thermodynamic deprotonation have switched around on that dichloropyrimidine.
Is there any way that you could do
The problem, I mean, yeah, I suppose there's, I mean, I haven't looked into this, but maybe there's some NMR chemical shift trick like we learned for EAS, and that could be used here, but I haven't seen anybody codify that yet. So the point is, if you have a heterocycle which you have never seen before, but the two positions are sufficiently differentiated, you could put, I would choose thermodynamic or kinetic conditions and try it out. Because, you know, dichloropyrimidine, you can cycle under that. But you may be encountering ones that have never been made before. And so you would just try to do two different, you'd know, I have a set of bases for kinetic and I have a set of bases for thermodynamic, and you try both. So there's no die-hard rule for some of the weird ones out there. Okay, how about this next one? Let's take that and treat it with N-butylene, or LDA will work just fine too. But let's just treat it with butylene and CO2. What do you expect the product to be based on everything we've seen here? Great shirt, Tanner. Have you been there? You should go. It's like an hour and a half. He's wearing a SpaceX shirt. What do you say? Just the regular product would be what?
Probably lithium halogen exchange.
Okay. Let's. That should happen really quick, right? Another possible product would be what? And it's possible to imagine that this thing would react to give you that, along with and it's also conceivable to imagine that B is sticking around for the ride here, and B metallates this one, but at the thermodynamically most stable anion. And then finally, when we quench with CO2, the product you get has the appearance of a dance. So the net product going from here to here, look what happened. This halogen has danced. It did a tango. It was literally a tango because it was intermolecular. This is called halogen dance. It's an extremely useful way to functionalize things on pyridines and other heterocycles too. But it's very difficult to teach. And so we'll spend a few minutes on it. But that's the mechanism. Now, all the glorious detail of halogen dance is outlined, I think, rather effectively in the book. So if you have time to look, here's section I on halogen dance. And that's the mechanism in a much more glorious detail than I have given you there, but it's the same. So the idea here is that, here is the example I just showed. You metallate here. There's then an initiation process. That dihalide intermediate is key. The dihalide intermediate then reacts with the product that you got from metallation. Right over there, I showed it to you, right? And then this one looks at this dihalo species and says, where am I going to do a halogen metal exchange there? And the halogen metal exchange takes place at where you're going to have the thermodynamically most stable anion, which would in this case be right in between these two because it's doubly directed. And so the net product you get is that with the appearance that this halogen is just shifted over one. That's why they call it the dance. You can do this in many different cases. So you can even do it, sort of across a ring, as we'll see. So look at this one at the bottom. We go from this, we treat this with a metal. And this one is an exception because the dance can't propagate. So you need to have a propagatable dance. So there's an example of where you can't dance. But when you don't have this issue, you can actually have dancing across a ring. We'll get to that in a minute. Across a ring, across a directing group is possible. So the rules for dancing. There's some more case studies here, but I think the one that we should start with is case study number 1. Okay, so there's your target pyridine. And in your mind, you might have all of these different retrosyntheses. Well, let's go through each one of them nice and slow. And if you need a coffee, no one's taken any. I don't know why. It's right there. Okay, so there's our intermediate. And you might say, well, I'm going to disconnect the methoxy one first, but the problem with removing this C4 methoxy or removing this C5 methoxy is how do you get the selective SNAR to happen? Right? Because if you do this, you've got this bromine staring you in the face. How are you going to do that? Same one. If you have an X here, how do you get selectivity between here and here? So when you make these disconnections, this happens in the course of maybe 10 seconds. You write all these, disconnect each one. You're like, can't do this one because I can't get differentiation. Can't do this one. The reason this one will go is because you got this para electron withdrawing substituent. And this one here, it may be difficult for you to differentiate between these two because this is a great directing group. So also probably not great. So the logical disconnection is probably going to be, let's just remove the bromine from this position. And then when we remove the bromine, our SNARs become easy because we don't have that annoying bromine anymore. So we can go down this path and say, oh, this methoxy comes from that. Should be no problem in the SNAR of that approach. And then this one comes back from here. We should be able to do some sort of electrophilic aromatic substitution. And this just comes from a displacement. Certainly viable. That would be fine on a test. You can also remove the other methoxy. That SNAR should work just fine with methoxide. No problem. And then how do we remove this one? Well, we should be able to get back either through metallation or maybe electrophilic bromination. And then finally, we get all the way back to this, which is just a methoxide addition. And that's what they actually reported doing. So in the forward route, you can do a chlorination of this pyridine, followed by methoxide addition. You can probably even buy this chloronicotinic acid derivative. You can displace that. You then do a directed metallation to go here, because eventually you need to go here. So watch what happens. We put the iodide here, because it's doubly directed. Then we treat this with LDA. It deprotonates here. It does a halogen metal exchange of its friend to make the diiodo. And then the most stable lithium is here, putting the iodide remaining here, and you get a net dance. Do you see that? I can go slower if you want. Now we're home free. Methoxide, SNAR. We only have one position that is really easy to deprotonate because we got double direction. Butyl, bromo goes there. And then look what we do here. You need to go to this position all the way across the ring. So there's only one position left to deprotonate. You deprotonate that with LDA. The LDA attacks its friend to make a dibromide. And then its friend that has just been lithiated says, oh, there's a dibromide there. The most stable lithiated is going to be here. So that bromine departs. The one is here still remaining. You quench with a proton, and that's your product. So they make it through two different halogen dances. Any questions on the halogen dance aspects of this route? That's a great point. So, Elena, right? Elena is asking about how many equivalents of base are they using, and that's a really important point that we glossed over. Namely, how do you promote halogen dance versus how do you squelch it? So if you want to promote it, you often use 0.9 equivalents of base. You usually never get 100% yield in these reactions. Usually around 60 to 70% yield for halogen dance. So you use low temperature. You don't use excess, sometimes 0.9 equivalent. You want to add your base to the halide to encourage this sort of dancing to occur. A solvent like THF, and usually a slow reacting electrophile, like CO2. And then if you want to prevent the halogen dance from happening, higher temperatures, large excess of base, do the reverse addition. So add the halide to the base. And that's how you can stop this from happening. So you have the option in these systems to do it or not to do it. Great question. Any other questions? We'll do more examples. Yeah, what do you say there? Chi?
So in this case, you will sacrifice half material for the hydrogen source.
No, because it keeps regenerating. You're not going to lose half. So the yield can be 70, 80% even. Because let's say after you do this lithiation, B has now been regenerated back to A. So B here took an iodine, and look what happened. I missed that part. Thanks, Chi. It's a propagating species. See what happened just there? It's a great question. I forgot to put that over the arrow. You want a coffee? It's confusing. This is confusing, right? Would you say this is really intuitive the first time, if it's the first time you've seen it? Do you get it already, like instantly? No. We have to do a few examples. I mean, maybe one or two you just know it. It's instant, easy, obvious. But for the vast majority of people, how often do you dance in MedChem? Haven't danced yet. Might you dance after this? I mean, the problem is Combi Block sells so many things, right? So they're having all the fun, waltzing, tangos, square dancing. They're doing all of it in San Diego in a big factory here, and so you guys don't have to. But one day you may have to dance, and then you'll be happy you were here. Okay, so how do we get all the isomers of this one? Dancing is optional. But now you know about the dance, you might want to do it. Oh, yeah. Lithiated is fine. Whatever you want. Let's put CO2 there. Why don't we put CO2? Let's see. Who do we have? Who have we not heard from? What do you say, Lucas? Any thoughts over there? You can just start us off. Sorry. It certainly will not. So what if I'm just going to give you LDA. And tell me what might happen just with LDA. Brilliant. Love it. So now if we just dump in CO2, isomer 1 is done. We're done with isomer 1. But what if we decide instead to quench it with iodo? Is there something we can do with iodo in order to get another isomer?
We do halogen dance when we move over to the 3 position.
Okay, we got the next isomer. Suggestions for our third isomer. You can use a trick we did before if you want.
Just make the 4-lithium TMS block.
Great. Thanks, Saul. And there's our third isomer. Now, I don't want you to get confused and say, well, wait a minute. 10 minutes ago, you taught us about the chlorine trick, and now you're why you don't like chlorine anymore. I still like chlorine. It's okay. If you wanted to, you could quench with chlorine here, and then lithiate here, and then remove the chlorine. That's okay too. That tactic has not disappeared from your toolbox. Okay, 2 more examples of halogen dance before we take a break from dancing. How about this one, the chloro CF3? What are we going to do there? What do you say, Jess? Sorry? Can barely hear you. I will get a hearing aid for the 2021 installment.
So first, just treating it with LDA would degradate to get the first isomer, and then treating it with iodine, and then do the halogen dance.
Or alternatively, is there another option we could do for this one? Could we put a chloro there? But how are we going to remove the C4 chloro versus C3 chloro? Do we know how to do that? Could you use palladium on carbon? Why not, Dongmin? You said no. Remove everything. Yeah. Is there another way to remove the mag? Yeah. You might be able to get away with, if you had the dichloro, you might be able to get away with using zinc here because it's C4. Probably won't touch the C3 one. So you probably can get away with that. I wouldn't risk it because you can have an HD. Why not do the HD, right? But technically, if you mark that on a test, it'd be hard to argue with because maybe it's possible the zinc would give you selectivity on the C4 if you quench it fast enough. How about the last one? Can we use the same trick that Saul taught us? Sure. Great. Done. I'm hoping that all of this was not obvious to you when you walked in the room this morning. All right, help me with this final dance. I'm going to take these 2 dibromothiophenes. I'm going to treat them with LDA and then an electrophile. What is the product? We'll take it stepwise. So in the top one, let's see. We have a thiophene crew. Gigi, Sarah, and Shuang. And all 3 of you are in charge of thiophenes and furans. Do any of the team members want to help with this one? All we need is just tell us the first step. What do you say, Sarah?
When you do
We'll start with this one. What do you want to do?
negotiate next to the
And what do you want the product to be? And then make the what? Sorry? You just want to quench?
So I guess you could also make the tribes.
Oh, I see. You mean in situ a dance is taking place and you get that? Is that what you're saying? It must not end there, does it? Because when you made this, you also made an equivalent of a lithium species somewhere. And the lithium species is going to look at this tribromo compound and say, I probably want to do a halogen metal exchange on you. And where might that base decide is the best spot to pluck off that bromine? Which do you think is the most activated? You'll have to remember the stuff we learned here. You'll have to remember the stuff we learned here and put it all together to answer this question. What's thermodynamically, you think, the happiest lithiated species? C2 is a great idea because you have this stabilization here, but C2 doesn't benefit from the extra little bonus stabilization of that bromide. So let's take it on. And then that converts to that. Now, maybe Gigi, the other enthusiastic member of the thiophene furan club, can help us with this one. Where do I deprotonate here? Can't hear you. Wait a second. When I do a halogen dance, doesn't it mean I go to this? I go to Sarah's compound, don't I? So that's why you get the same product. Both of them give the same product. Are you guys happy with dancing? It's a hard concept, which is why in 2 weeks, David and Yuzuru are going to give 1,000 more examples until you can dance in your sleep. Okay, so how do heterocycles like to react with radicals? They actually have a voracious appetite for them. And a good example of this is the synthesis of this ergoline ring system illustrated here. And the key disconnection one needs to make is a radical one. Namely, these coworkers decided to disconnect here. Now this unit is going to become that. Problem, Yuzuru?
You solved the question of the day.
Oh, no.
No.
It's still, they still need to tell us what the combination does. Don't worry. What's that? I need more than coffee, you sure? Okay, so we start with the 4-bromo-indole, and we treat 4-bromo-indole with KH, followed by T-Butylate, quench it with boron, then acid, and then finally Suzuki. So what happens here? The KH does what? The KH protects the nitrogen, doesn't it? So the first thing that happens, then what does the T-Butylate do? Then we put a boron here. And then the Suzuki happens to give you A. Oh, it doesn't give you A. It gives you this indole here. And then after you treat with oxalyl chloride.
Mix oxalyl chloride.
What's that?
There's 2 carbenes in oxalyl chloride.
I didn't draw that. Did you draw that, Yuzuru?
No, wait.
Do you need a coffee today? There's no way I did that. That definitely, yeah. The video wasn't rolling, so we may never know. Okay, so with compound A in hand, we have problem of the day number 2. So problem of the day number 2 is taking that intermediate oxalate and treating it with that concoction of reagents. We need someone, the only people who would know this one have to be hardcore organometallic people because it's so complicated. Where are the... Let's see, we've got some... we have some Jinquan people, we've got some Curie people. Lucas says he wants to do it. All right, great. He's going to make Curie proud. You're all taking organometallics. Super complicated organometallic mechanism. Make sure you know all your orbitals with this one. So first, I guess, let's identify the valency of the silver. Is it silver 1? Is it silver 2? What is the role of the acetic acid? What's going on with all this concoction? Silver nitrate is silver 2? So the S208, what's the fate of that? It's your oxidant, but S208 turns into what? What, somebody said it? But they're just whispering. They just want to whisper. What? Sulfate. Okay, so you can draw that out. S208 goes to SO4 minus 2 of those. Okay, great. Now, what's that silver going to do? You got that radical there. Great. And then what does that do? Decarboxylate. Oh, and he's already put the proton on the pyridine. Great. And once we get that radical, nice. Well, you flipped it. This is interesting. So you're gonna give us the adduct, the opposite regioisomer, which is usually a question I get every year. Why does it go C4 and not C2? Yeah, so it's good. Lucas is drawing the regioisomer of the product, which is fine. Yeah, that's okay. I mean, we can stop there because we see the product. The product I drew out already. And so the reason is because of an electronic bias. That, and this is often the problem with Minsky and related radical reactions, is that they do give mixtures, and those mixtures are often solvent-dependent and context-dependent. And it is possible to modulate regioselectivity of these radical reactions by changing your solvent. Donna's group and our group had a paper on that many years ago talking about that. But the point of this is to show you the power of Minsky chemistry. So, yeah, you add into the heteroaromatic that's charged, makes it super electron deficient, great radical-ophile. These reactions can be done with water, co-solvent. They take place often in the old manifestation. They need higher temperature, but in the newer ones, you can do them at room temperature. And Minsky has sort of found a new renaissance, I guess, in industry. Lilly and Pfizer folks, you guys ever do Minsky type stuff? Yeah. All the time. So, okay, great. That means what I'm teaching you is relevant. Unlike halogen dance, which is completely irrelevant, I guess. Okay, great, Lucas. Yeah, we're good. Thank you. So you can make Minsky functionalized to give you these types of adducts, and this just comes from pyridine via proline and carboxylic acid under the exact same conditions. That was a Merck process paper. You can make this one, again, from pyridine. I won't draw that, but you can use even a boronic acid is known under Minsky conditions will give you an arrow radical, surprisingly. These guys can be made from what is known as these weird sulfonate salts, which can be zinc or sodium. You treat those with a mild oxidant like TBHP, and they turn into radicals. And you can even make these strange adducts just by using dioxane, just by using iron salt and like TBHP, so-called Fenton-like chemistry, because these CH bonds are really weak when you have them alpha to a heteroatom, so it's very easy to make those radicals and they just add in. So for med chemists, this chemistry is a dream, because at the end of your sequence, you can just take your scaffold and Minsky the hell out of it to get you alkyls, fluoroalkyls, whatever you want. And often the regiochemical quagmire that might disappoint the process chemist is welcomed by these folks because they just want to explore SAR really quickly, and getting a mixture of 2 or 3 regioisomers is bonus time, because then you don't need to go back to the beginning and make the whole thing from scratch. So there's a lot of benefit to that. Let's talk about what happens when you add electrons into electron-deficient rings. We talked about radicals, but let's kick it up 1 electron. So let's add in a 2-electron species. So if you take pyridine and you add in, let's say, just sodium, what do you think might happen there? The product of this is a dimer, but what type of dimer? And in the case of nickel, the opposite regiochemistry is observed. The reason for the nickel is probably there's a chelation effect taking place. And this one is a really useful one because if you treat it with methyl iodide, you get what's known as paraquat, which I think was used commercially as, it may still be, you can buy it at Home Depot as an insecticide or some sort of agricultural agent, paraquat. I think you can still buy paraquat from Home Depot. How about the addition of carbenes to electron-rich rings? So you can add carbenes to electron-deficient ones, but what about carbenes to electron-rich ones? And this one is known as the Chiamen-Sen-Denstedt reaction. I didn't name it. Don't blame me. How does this one work? We need the pyrrole crew, max or max.
Add across C2, C3, and then just break the propane, kicking out of chlorine on the way. Break that internal. Yeah.
Great. And so max is very well prepared for problem of the day number 3. It should take you 2 minutes or less. You might even be able to just call it out.
So with one chlorine, it's exactly what we just did.
Can you put it up there so we know what he's talking about? There we go. Yeah, that's what happened there. We got this dimethylindole. So one of the products Max already called out. So why don't we just draw his key intermediate, and he can just tell us. So one of them led to the canonical Chiamen-Sen-Denstedt rearrangement. And what about the other one? So the regular product would be here, but what about the other one?
I'm having trouble writing with this type. However, just kick, turn away.
Yeah, almost there. That arrow is good. Yep.
Can I just make this anion?
And it just quenches.
Yeah.
You got it. Does everybody see that? So the product of that reaction, the other mysterious product in problem of the day number 3, is just that. Another example of carbene addition to electron-rich ring is from Yu Davies' group. They had a lot of papers on this topic. This is making the cocaine ring system. Just take a pyrrole, does a cyclopropionation, followed by a cope rearrangement. I don't need to talk about cope because you all had Shenby's class, so you can figure that out really quick. And that gets you the tropane core really quick. Addition of carbenes to electron-deficient rings. You know, you don't see this very often. It's usually to make reagents. So you can get this adduct by just adding a sulfonyl azide species. And you can get this adduct just by using a regular carbene. The point here is that it reacts at the nitrogen, not surprisingly, right? It's not going to react at the carbon. Whereas the electron-rich systems, they react like olefins, just like they're more prone to do Diels-Alder. Same concept. Okay, let's talk about the effect, or maybe before we do that, let me just remind you that so far we have talked about a lot of things over the last 2 lectures. We've talked for the last 3 hours. We have talked about electrophilic attack at nitrogen and at carbon. We've done both of those. We've done nucleophilic attack at carbon. That was yesterday. So attacking and being the aggressor and being attacked. We've talked about reaction of radicals and carbenes just now. We talked in lecture 1 about aromaticity as a rough guide for reactivity. And we've only got about 14 minutes left to cover the rest of general reactivity. There's not much left. Now let's just talk about, very quickly, how does electron withdrawal of a heterocyclic system affect the reactivity of your substituents? So, easy, hard. What? Well, nucleophilic displacement. We know this already, right? We talked about this ad nauseum. Having a chloro there trying to do an SNAR, right, Chang? Don't do it. Don't do it. Whereas over there, super duper easy. Proton loss. You know, the Vincent maneuver. Right? Fits in here really well. Decarboxylation also follows this trend. Michael addition. Hey, Cheng, if I add thiophenol into a mixture of these 2 compounds, which one is going to react? One-to-one mixture, I add 1 equivalent of thiophenol. The only observed product from such a reaction would be this. In fact, there was just a paper a few days ago on using vinyl pyridines as cysteine covalent reactive groups. You know, the vinyl pyrrole is just going to sit there and look at you. Not going to do anything. Right? Just this is when I see this, I see okay, it's butadiene. When I see this one, I see methyl vinyl ketone. Remember pyridine, the schizophrenic heterocycle? So this is just methyl vinyl ketone hiding. I can't take a 3-vinyl pyridine and do the same thing. Right? It needs to be 2 or 4. Great. We got a great example of how substituents can affect reactivity in remarkable ways from Boger's synthesis of Frederikomycin. So front page of your handout is this really awesome looking compound. And in order to solve this problem, we do require a Boger group member. Because I guess I'm assuming that before you join Dale's group, you have to read his 800 papers before you join and take a cumulative exam on the is that correct, Max? Do you have to do that? Gigi? You're not finished. Still working on it? All right, Gigi, why don't you tell, because you already read this paper 100 times, and what happens here? Great. And then what? Hey, what do you mean deprotonation on methyl? How can I do that? Can I deprotonate toluene? That's ridiculous, right? But somehow you're just telling me deprotonation of methyl group like nothing is wrong. Can you just explain why that was easy for you?
That's because that's the only position, only methyl can be deprotonated.
Well, that's not. I mean, if you told one of my kids that, they wouldn't understand it. So.
Would your kids understand resonance stabilization on anionic nitrogen?
Nope. But
The point still stands.
Yeah.
I couldn't understand what you're saying.
Well, the reason I say this is because LDA, we could argue it would go here. Why did you choose to go here? Because that position looks like a ketone, and ketones are easy to deprotonate, is what my 10-year-old would probably maybe understand a little bit better than that's the only position. So we deprotonate, and the product of that is this. And Gigi, what happens finally? And then Claisen. We're done. Look at the structure of Frederikomycin. Not too far from that. Same thing has been used on process scale. Look at the synthesis of Singulaire. This was by Merck back when Merck Frost existed in Canada. Canada used to be the best place to do drug discovery. All the companies were there, and now I think they're all gone. Just little CROs there. But you know, the Merck site is actually probably the most prolific. The Merck site in Canada was the most prolific one, led by the med chemist legend Pepe Percite, who helped invent Singulaire and also Vioxx. It was all done in Canada. And the Vioxx still a good drug, even though they took it off. Don't tell Eric Topol I said that. Anyway, Singulaire. So we treat this compound just with the aldehyde and, kind of weakly basic conditions, acetic anhydride. Look at the structure of Singulaire on the front page of your handout. It's right there. What happens? Just one word. Just say one word. What? Aldol. That's it. Because this is basically a methyl ketone. And if you take a methyl ketone, I think that's probably something all of you did in undergrad. In the undergrad lab, didn't they have you do aldols? And then take melting points to get the unknown? You didn't do that? No? I did that. Now let's look at the back of your handout for dabrafenib. This is a really cool kinase inhibitor. Sorry, Saul. And if you look at the synthesis here, look at this middle step. Let me ask the medicinal chemists here, would you make dabrafenib by breaking this bond here through a Suzuki reaction as your first disconnection? Patrick and Ren, would you do that? What's that?
Seems reasonable.
You think it would seem reasonable to do a Suzuki coupling there?
Yeah.
By today's standards, perhaps. But nobody did it. The med chemist didn't do it. And the process chemist also failed miserably at doing that. And so the discovery route was actually making this ketone and then forging the thiazole, because that's a really tricky thiazole to make the boronic acid. I don't know why they didn't try stili. Anyway, this pyrimidine chloride can be deprotonated just like a methyl ketone. Add in there, do a simple Claisen, and then ring synthesis that we won't talk about for a few weeks. But that key step of dabrafenib is worth remembering in this context. So, problem of the day number 4. Looks like we're running out of time. We're going to have to go quick. Luckily, I've saved you time on problem of the day number 4. I put the 3 commercially available building blocks we're going to be able to use for problem of the day number 4. Problem of the day number 4 is asking the question, how do you make that diamino bromo compound? And maybe due to lack of time, we can have this problem of the day done in a group-like fashion. Hannah, what do you think?
Sorry? What do you mean by group-like fashion?
Well, should people just offer suggestions? I need to make these 3 compounds eventually turn into this. So using starting material A, how would you do that? Okay, add an ammonia. And what's the potential liability of doing that? Wild mixture of misery is the answer. Mono, bis, tris, mixtures of bis, mixtures of mono, not good. So A is probably not a great way to go. Certainly not, I mean, if you put it on a test, you get partial credit, but gee, we'd hope you could be a little better than that. This is a second one is called chelidonic acid. That's when you check SciFinder, you'll find you can get kilos of that stuff. How would I convert that into B? What? Hoffman or Curtius, let's say. So you could treat B first with POBr3 and then Curtius. And that would give you the product. Problem is you got to do POBr3. Curtius times 2. Curtius is not something people want to do on process scale. You'll find LPRD papers where they do flow chemistry. They do it. Sometimes they do it, but they really don't want to have an acyl azide on scale. Med chemists love Curtius, no problem. But process chemists really don't like it. How would I take C and convert it to the product? Using what we learned yesterday. It's a great point. That's a great point, Elena. The issue with this, so let's say we go ahead for the jugular, and we make this directly just by boiling in ammonia. And then you're saying do an Friedel-Crafts there with a bromo, right?
Yeah, I guess you get more ortho.
It's going to go ortho is the problem. So we need to do something a little bit different before we do that. Aha! N-oxide. And then what? What will go at the 4 position? So if you put a bromo now. And then guess what? When you add ammonia to this, it only goes once and then twice cleanly, and it stops. And then you can just treat it with a very mild reducing agent to remove the N-oxide.
Why brominate this way instead of just starting from A and treating this from A?
Why brominate? Say that again. Why?
You can intercept the same tribromopyridine oxide just by.
Oh, yeah. Apparently, that compound is just not electron rich enough to do that. And to be further frank with you on this, they don't brominate here. They do something a little bit different than that. Straight out of yesterday's lecture. Do you remember when we talked about cylindrospermopsin? What did they do with cylindrospermopsin? Nitration. So in order to get this bromo, they go through the nitro. Then they treat that with acetic acid, acetyl bromide, and they get out the bromo derivative. And going straight to the N oxide by the tribromo, I think it's because it's too electron deficient, doesn't form the N oxide very well. Okay, almost done. Problem of the day number 5 is our last problem of the day. And the last part will only take us, we'll probably run over by 5 minutes. So problem of the day number 5, this should be one that you can call out, but we need the imidazole people to help us with it. So Chang or Nick, I don't see Nick, so maybe Chang can help us with problem of the day number 5.
So first, we will coordinate the acid between the two nitrogen.
And then? Well, look at all the positions you can deprotonate. We can deprotonate here, potentially here, potentially here. So what are you saying happens?
I think first happens the mass will between the two nitrogens. That
Sounds good to me. Great. Told you that was a quick one. Finally, the last thing we have to cover in the last 3 minutes before we get to the free consulting here, which will be quick, is the electron donation effects on substituent reactivity. And we talked about this already. Steve had the answer in lecture 1 for the chlorophyll synthesis. Do you remember when he treated that 1 nucleophile on the 2-chloroethylpyrrole and it made a quinomethide type species? Same thing here. This is the very first synthesis of tryptophan. It was a landmark back in the 50s, I guess, when it was first done. The first step is a simple formylation. Manic reaction, basically. And then when I treat this with, by the way, this has a name. Back in the old days, they used to call these things, if you see them, they call these gramines. I don't know why they're called gramine. Maybe someone can look into that. But gramines, when you treat the gramine with base, Steve, what happens? Well, sorry, this, not with base, but this deprotonated malonate species. Squinting. You should sit in front. Does this just do a SN2 on here? Nope. Cleanly to that, and then the remaining anion that's sitting there adds in. And then after decarboxylation, you get your decarboxylated tryptophan acetylated. And the final question that apparently was an interview question for Saul when he went to Gilead was LAH on that indole. And how did you get the job, Saul?
You first reduce the alcohol, eliminate the quinomethide, hydrolyze it.
Same thing. So remember, the effect of a substituent, don't forget that. The additive effect of pushing on the potential leaving groups. That probably happens to the illuminate species you have, not just the free alcohol. Okay, and the free consulting here, this one's from Lily. We found a nice paper for you. You know, this one is probably best accomplished just by using reductive, so you cross electrophile. So you would use nickel and a reducing agent such as magnesium or zinc, and that should very cleanly give you the coupling here. And our TAs will send you the paper, the appropriate paper for this. But that's probably the simplest way to go. Do we have any other alternatives that we came up with? No, that was the first thing. That we'll send you the. It's pretty good precedent for this. I think it should work well. But if it doesn't, let us know. Yeah. Okay, great. All right, guys. Well, I'll see you next Wednesday for our first ring syntheses. Finally. Where? Which one? It is, yeah, that's a good question. Why is it?
But I was thinking you could also add in here to the S2, right?
Well, I don't. Okay, so it's a good point. Is it reversible? If it was a thermodynamic situation where added in a ketone and then it reversed back, and then the only thing that drives it to the end is Claisen is one answer. But I don't know. I would go with hard soft, but I can't rule out that it just adds into the ketone, reverses, and then gives you 1,4. Yeah.
I was just wondering if there's a way that you could
I think if you were to add cerium, then you may. First thing I would do is change this to KHMDS instead of LDA, make it harder, and then add cerium.